So here's a question from 2018, and this is on the analysis of a second order system. And for this second order system, we've been provided with a simple control signal flow graph. And as you can see, we have an input x of s coming in one side, we have an output y of s coming out the other. The forward path in this controller is comprised of an element g of s in series with p of s, and then there's a feedback path f of s, which gives negative feedback to this system. We're then given the transfer functions of the various parts. The p of s is just given by the plant, which is 1 divided by 2s plus 24. Transfer function of this g of s pre-processing part, which could be some kind of controller, is given by k1 divided by s. And we're told that the feedback path f of s is given by just the constant k2. So we're asked, first of all, to calculate the closed loop transfer function of this system, which is y of s divided by x of s. And after we've done that, we plug in values of k1 equals 1200 and k2 equals 1, and we evaluate it. Then we're asked to evaluate this or express this in canonical form and write the expressions which we can get by inspection for the natural frequency of this system and the damping ratio zeta of this system. And then given that we can say something about the damping ratio, what regime of damping is this system operating in? Then given the fact that we've got the damping ratio zeta and the omega n natural frequency, we can use formula to directly calculate peak time, percentage overshoot and settle time when we give it as a response to a step, because the formulas will relate directly to these characteristics for a second order system. You're not expected to remember those formulas, you would be given them in an exam. Finally, we'd asked to sketch what a typical step response would look like that exhibits rise time, peak time, percentage overshoot and settle time, and actually point the things out on a drawing. So let's start off by doing the analysis of the system in terms of transfer function of the whole closed loop system. I've drawn the question up here on the right upper side just so we can have a look and see what we're doing. First thing we want to do is look at the open loop response of the system. So we just ignore the feedback path f of s, and we see the feed forward path, right? The feed forward path at the top is given by the signal going through g of s, then going through p of s. So two things in series means we can replace we can replace that with a single block corresponding to the product of those transfer functions. So the open loop transfer function is gs ps. Then we're going to substitute in the values that we've been given for p of s and for g of s. So it's going to be g of s k1 divided by s multiplied by 1 divided by 12s plus 24, and that gives us the open loop response transfer function. To calculate the closed loop response, then we basically use the formula that the closed loop response is given by the open loop forward path divided by 1 plus feedback path transfer function multiplied by forward path transfer function. And all we have to do is substitute in the values that we've got. So this open loop part is what we just calculated up here. It's the k1 divided by s, 12s plus 24. Then we have the 1 plus, same thing again, but this time is multiplied by the feedback transfer function, which is k2. Then what we want to do is simplify this expression, and the easiest way to do that is to multiply through the top and bottom by this denominator term s, 12s plus 24. Then it will disappear here, it will disappear here, and it will reappear here. And as long as we're at the top and the bottom, we're not affecting the actual value of the equation. So that gives the quite simple expression. The closed loop response is k1 divided by s times 12s plus 24 plus k1, k2. And then we just want to stick in k1 equals 1200 and k2 equals 1. And there we have the closed loop transfer function of this system evaluated with those constant values. Right, so next thing to do, what we're actually going to do now is we're actually going to multiply it out. and we're going to write it in such a way that there is no, there's a unity factor in front of the s squared, so we have to divide through by 12 in order to do that. We divide at the top and the bottom by 12, and we end up with 100 divided by s squared plus 2s plus 100, which is a nice clean result. We're now going to compare this with canonical form, and if basically we were saying that this transfer function that we've got here has got to be equivalent to the canonical version. Let's not worry too much about the top bit here. But the canonical part, basically, we can concentrate on what happens at the denominator. And as you can see, we can represent that by the canonical form, in which case we have a unity in front of the s squared, which you've got already. In front of the s, we have 2 zeta omega n as the scaling factor, and in terms of the constant term, we have omega n squared. And in this case, we also have omega n squared at the top as well, which also represents this value here. So we can directly look at this, and by inspection say we can see that omega n squared is 100 if we compare the two things together, which means omega n for our system has got to be 10, and 2 zeta omega n is equivalent to 2, so obviously zeta omega n is equivalent to 1, so therefore if omega n is 10, zeta has got to be 0.1. So we've already, by inspection then, examined this equation, and we can immediately say what omega n is, which is the natural frequency, and also what zeta is, which is the damping ratio of the system. So this is a very nice way of saying something by inspection about the characteristics of the system and how it's going to behave. So, well, first of all, what regime is that going to be in? 0.1, right? So the regime between 0 and 1 is going to be underdamped. Okay, so that's what we need to point out there as well. The peak time we will be able to look up from a table of basically a formula for this kind of second order system, and it's given by pi divided by omega n square root of 1 minus zeta squared. What we'd have to do is just plug in the values that we've got. So we stick in the omega n as 10 and the zeta as 0.1, and we calculate it, and in this case it would be 0.3157 seconds or so. Percentage overshoot is given by the formula 100, because it's obviously percentage, multiplied by e to the power minus zeta pi divided by square root of 1 minus zeta squared. Again, you'd get that from the formula. It's just to make sure that you know where to put the numbers in. If we evaluate that, we see that we end up with 72.9%, and the settle time would be given by 4 divided by omega n zeta, stick the values in, and we end up with about 4 seconds on that one. So where is the rise time going to be on a system? Let's draw a response, which is, as you can see, this is, in this particular case, this is obviously not critically damped. It's not critically damped. If it was critically damped, what we'd have is we'd have this rising up as fast as it can, but not overshooting at all. If it was completely underdamped, it would be oscillating like crazy. We've got it underdamped here, so it's the damping is less than 1, but it's not oscillating, so it's definitely more than 0. And so when I say if it was 0, it would be continuous oscillation with constant amplitude. So it's somewhere between critically, it's more than critical damping, in which case you get no overshoot, and it's less than a continuous sine wave, is when you get damping of 0. So this is in the regime that we're actually finding the system in. So 0.1 is going to be between 0 and 1. So this is a typical example of what you might get. Let's say if damping was about 0.5, I'd something like that. So this exhibits the kind of things that we're asking in the question. It exhibits, first of all, it's got a rise time. So it's rising up here. It's got to have a peak value that overshoots, and it's going to take a little bit of time to settle down. So let's think about what's the rise time defined as. Well, it's actually defined as the time between the value getting for 0.1 times the final value to 0.9 times the final value. And if we're driving this thing with a step and it actually gets there, then the final value is going to be 1. So in this case, it would be the time between, how long does it take to go between 0.1 and 0.9, and that's given by, that's called the rise time of the system. Peak time is, how long does it take from the start to get to the peak value, and as you can see, the peak happens when we get the big overshoot and then it comes down. So this is the biggest the biggest output the system is ever going to generate, so we want to know the time to that. So that's how you'd mark that onto the drawing. Peak overshoot is basically how much it goes over the steady state value that it's going to get to. In this case, if this is a scaled step response and it ends up getting there, it's going to be how much it gets, how much more is it than the actual value that it ends up at. So how much is, what is this little bit here representing? That's the overshoot from where we wanted it to go to. And finally, settle time is how long it takes to get within 2% of the final value. So continuously, so consistently. So here it shoots flying past it, and here it comes down and goes underneath it. And then here, at this point here, it's now within 2% of the final value, and it never gets further away again. So this time to there is the settle time of the system. So it's now basically settled down to within 2%.